So, in order for us to have an example that we can use to explore thermodynamics, we need an equation of state for a particular substance. An equation of state is an equation that relates the state variables of a substance to each other in equilibrium. We're going to be looking at an ideal gas, so we'd like to answer the question, how are pressure, volume, and temperature of an ideal gas related to one another? So we'll consider a cylinder with a piston trapping our ideal gas. And we're going to ask, what is the pressure that is exerted on the piston by this ideal gas? How much pressure is exerted on the piston? Well, as we know, pressure is equal to force per unit area. We'll take the area of the piston as A. And so all we need to do is determine the force that's being exerted on the piston. Okay? Well, in order to determine that force, we need to consider why there's a force being exerted on the piston. Well, the reason why is because these gas molecules are all moving around, jostling around, bumping into each other, and, by extension, the piston. So if one of these gas molecules comes up and hits the piston, it will reflect off of the piston, and in doing so, its momentum will change. Okay? The piston, in this way, acts to change the momentum of the gas molecules. And as we know, a force can be understood as a change in momentum divided by a change in time. I'm going to write these as vectors in this equation just to distinguish the P for pressure from the P for momentum. Okay? Those are not the same quantity. They're related in some way, but they're not the same. Okay? All right. Now, because we're looking at gas molecules, these are going to be elastic collisions. If it was an inelastic collision, then that would mean that the quantum state of the molecule was changed as a result of the collision with the piston. Now, a gas molecule got to hit a piston awfully hard in order to promote its electrons to higher energy levels. Okay? We did not throw the nitrogen molecule at the piston so hard that it broke apart into two nitrogen atoms. All right? These are elastic collisions for that reason. So here, the components of the momentum that are not perpendicular to the piston are left unchanged. All right? Only the vertical component that's changed, and it will reverse its direction. Okay? So for that reason, the momentum that is imparted on the piston in the short time interval delta t is going to equal, well, let's see. All right. So I've got gas molecules with mass m, and I can look at the z component of the velocity, vz. Okay? It started with a z component of momentum mvz, and it ended with a z component of momentum negative mvz. So that means that the momentum that was imparted on the piston, which, by the way, will be absorbed by these pins that we're putting in the piston in order to prevent its motion. All right, so the piston's not actually moving, but we can still analyze how much momentum is imparted onto that piston, and it's just going to be 2 mvz. All right? Two mvz times the number of molecules with a z component of their velocity, vz, that hit the piston in time delta t. Now this is only the momentum imparted on the piston by gas molecules whose z component of velocity is vz. So if I want the total momentum, then I'm going to have to sum over all z components of velocity, vz. Now, I have to be careful. Vz has to be positive, right? If the gas molecule was going down, well, it ain't going to hit the piston in time delta t, which, of course, we're thinking of as a very small time interval, delta t. All right? So I really should only have Vz positive. All right? Now, how many molecules are going to hit? Well, if the z component of their momentum is mvz, the z component of their velocity is vz, then they will hit the piston in time delta t if and only if they are close enough to it. Well, how close do they have to be? Well, I mean, in order for the gas molecules to hit in time delta t, they have to be closer than Vz times delta t away from the piston. Okay? So every gas molecule with z component of velocity, Vz, lying in this volume of the cylinder will hit the piston in time delta t, thereby contributing to this momentum that is imparted on the piston. So we'll have a sum over all the VZs greater than 0, 2m VZ. And now what we're going to argue is that it's no more likely for a gas molecule to have z component of its velocity, Vz, here than here. All right, so the number of molecules that are going to hit with z component of velocity, Vz, is equal to the fraction of the volume of the whole container that this piece represents times the number of molecules with z component of velocity Vz in the whole container. So I'm going to have this volume which is AVZ delta T divided by the whole volume times the number of molecules in the whole volume that have z component of velocity Vz. Well, that's going to be the number of molecules in the whole volume times the probability that the z component of the velocity of any particular molecule is Vz. All right? So this gives us the total momentum that is imparted on this piston in time delta t. We want the pressure. Pressure is force per unit area. Force is momentum imparted divided by delta t. So the pressure is going to be this quantity divided by A delta t. Okay? Now, I'm going to go ahead and pull the 2 and the N and the V out front. All right? 2N over V. And then I'll have the sum over all positive VZs, and it'll be VZ squared times the probability that the Z component is Vz. Now, clearly, the probability that the Z component of the velocity is positive is the same as the probability that the Z component of the velocity is negative. All right, so rather than always writing, I only want to sum over positive Z components, we could say, well, let's just take half and sum over all the Z components. All right, so that's going to be all right. Now we can further simplify this by arguing isotropy. This gas is isotropic. That means that it's the same in all directions. So there's nothing special about the Z direction all right, in comparison to the x and y directions. That's true. Gravity, we can say, acts in the z direction. And that will make a big difference if we're considering the probability that the gas molecule is going to travel kilometers vertically. All right? But if we're just looking at a gas trapped in a cylinder where it's not able to travel vast distances up, that gravitational influence is going to be very small. So we're going to ignore it. Okay? It does not make a large difference. We can talk about the effects of gravity on ideal gases later on. But for right now, let's just ignore it. Okay? So, with that assumption, the velocities are isotropic. They're the same in all directions. So rather than only considering the square of the z component, we could consider the square of the whole speed, which is vx squared plus vy squared plus vz squared. And that would be 3 times just vz squared by itself, because each of them are the same. So I could view this as 1/3. All right? And then, of course, so we're adding up over all speeds, mv squared times the probability. Now, of course, at this point, we recognize that mv squared is so close to a quantity of significant interest to us. The kinetic energy, which is 1/2 mv squared. So I can say pressure is equal to the number of molecules divided by 3 times the volume times 2 times 1/2 mv squared. And this is something that we've already been talking about. I'm adding up over all possible values of something, the speed, value of the kinetic energy times the probability that it has that value. As we've already discussed at length, this is an expectation value. All right? So we're saying the pressure, and I'm going to go ahead and manipulate it a little bit. I'm going to multiply by V. So I'll get PV is equal to N times 2/3 of the expectation value of the kinetic energy. All right? PV is equal to N times 2/3 the expectation value of the kinetic energy. Now, we've already seen this law, of course. Experimentally. determined that gases, far from their liquefaction points, when they behave more or less ideally, satisfy this equation. Where lowercase n and uppercase n differ because uppercase n is the number of molecules of gas, while lowercase n is the number of moles of molecules of gas. So if I wanted to change that over, I could say the number of moles is equal to the number of molecules divided by Avogadro's number. All right? The ideal gas law constant R divided by Avogadro's number is a more fundamental constant called the Boltzmann constant. All right? Its value is approximately 1.38 times 10 to the minus 23rd joules per Kelvin. Let me get a better value than that. 1.3806,488. What did I say? 06488. All right, and then we have an error in parentheses. That 13 means that the 88 at the end could be as small as 75 and as big as 101, or it would be 501. Okay? We're going to use essentially 1.38 for all of our investigations, but this is the value as of a few years ago. Okay? 7 years ago or something. We could look up a better one, but whatever. All right. So this, of course, is joules per Kelvin. That is to be compared to the ideal gas law constant, 8.31447 joules per Kelvin mole. All right, and of course, we have to make sure that we work with SI units rather than the chemistry people units, where it's 0.08206, something like that, liter atmospheres per Kelvin mole. Okay? So we just have to make sure that we use the right one. We'll be working with SI units, so we should work with this 1.38 times 10 to the minus 23rd joules per Kelvin. Comparing these two, we see that the expectation value of the kinetic energy is equal to 3/2 K Boltzmann T. All right? Now, if we look back at our analysis to see where that 3 came from, we find that it came from the fact that the gas molecules can move linearly in 1, 2, 3 independent directions. All right, they have 3 ways in which to use kinetic energy. So this gives us a concept of equipartition. Of energy. The energy is distributed equally, on average, to each of the degrees of freedom. Each way of using energy gets 1/2 K Boltzmann T of energy on average in equilibrium. All right? So we can use this to write down an expression for the total internal energy in an ideal gas whose molecules have L degrees of freedom. Using the equation of state, or the ideal gas law, we find that the internal energy of an ideal gas whose molecules have L degrees of freedom is L over 2 times PV. L over 2 times the pressure times the volume. Now, if the gas is monatomic, like helium or neon, then L will be 3. 1, 2, 3. But diatomic gases have other things that they can do. So a diatomic gas can, if the temperature is high enough, also rotate around like that, which is a separate degree of freedom. So now we're at 4. They can also rotate like this. Now we're at 5. It turns out that because of quantum mechanics, the energies are quantized, and that first leap to get to the first excited state where it can spin like that, too expensive. You can't afford that. So it doesn't get to do that. All right? So now we're at 5. That's the number of degrees of freedom nitrogen molecules experience at room temperature. 5. If the temperature goes up a bit more, then diatomic molecules can also start to do this. That gives us 2 additional degrees of freedom. One associated with the kinetic energy of vibrating back and forth, the other associated with the potential energy of vibrating back and forth. So that gives us 7 degrees of freedom. Chlorine gas, with its weak bond, exhibits around 7 at room temperature, maybe a little bit higher. All right? So with these results in hand, we can explore some processes that an ideal gas can be forced to undergo.